Hello everyone, welcome back to another video of Married Maths, and today with Laplace's best friend. It turns out that this guy called Simon Pierre of Laplace sent me from the past to come here and show you how to solve this differential equation using his own method. He was like, take this Married Maths and show your followers and your students this method of the Laplace transform. So essentially what we're going to talk about, right? I think this is the first time I talk about Laplace transforms in this YouTube channel, but we're going to solve the initial value problem for this differential equation y quadruple prime minus y equals 0, okay? Given that y of 0 is 0, y prime of 0 is 1, y double prime of 0 is 0, and y triple prime is 0. So given that, we're going to find what's y of t using the method of Laplace transforms, essentially. But first of all, we have to make sure that whatever solution we find, y of t, right, it has to satisfy a very specific set of conditions. Now, what are these conditions? Well, suppose that y to the power of 1, right, so y prime, and y to the power of n minus 1, okay, all satisfy a specific set of conditions. So, first of all, they can be piecewise continuous. Piecewise continuous, okay, so that means it could be something like this. It can be a function like that, right, and then it's going to be jump like that. But the essence of this, it has to be piecewise continuous. Okay, this function is continuous, but it doesn't mean that it's not differentiable, right? At this point, clearly the function is not differentiable. However, it's still continuous, right? Because the limit from the left is not equal to the limit from the right, therefore it's not continuous. However, the value of the function is defined at this point, but not at this point. So this is what it means by piecewise continuous. So these three have to be piecewise continuous on the interval. We're going to call it, okay, interval from 0 to a, some constant a, okay, t is between 0 and a, and we're going to say that there are constants k, a, and m, okay, that exist on this interval in such a way that the absolute value, okay, of the function y and the absolute value of the function y prime and the absolute value of the function y to the n minus 1. So what I mean by that is the absolute value of y of t, comma, absolute value of y prime of t, comma, absolute value of y to the n minus 1 of t. All of these functions, okay, they have to be less than or equal to the constant k times e to the power of at, okay? For all values of t where it's greater than or equal to the constant a, okay? But of course, this has to apply for the interval from 0 to a, right? Where t is between 0 and a. So this is called corollary 6.2, which is on the textbook that I'm using. So that's just a corollary, right? And then from that, we can say that therefore, if we take the Laplace transform, of the function y to the power of n, right? It's not a power, excuse me. The nth derivative of the function y with respect to t, okay, this is going to be nothing but, okay, it's going to be the Laplace transform, okay, of y of t, right? So now the idea is to rewrite this in terms of the Laplace transform of just y, right? The first derivative, the 0th derivative. It's just the function itself, y of t, the one that we want to find, okay? So it's going to be this, multiplied by s to the power of n, okay? And now we're going to subtract, okay? We're going to subtract y, okay, y 0 times s to the power of n minus 1, okay? And then we keep on subtracting things, so we do minus dot 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 minus, and then we're going to have y to the power of n minus 1, okay, power of n minus 1 of 0 times s to the power of n minus 2, okay, and then minus y prime of 0, okay? So using this method, we can find what is going to be the solution to the differential equation, okay, if we find the Laplace transform of the nth derivative of y. So now let's use this theory to apply it to the initial value problem that we have in front of us and see what we can get. Okay, so we have y quadruple prime minus y equals 0. So what we do is basically take the Laplace transform on both sides, knowing that the Laplace transform is a linear operator. So what I mean by that is, if I take the Laplace transform of the left side, which is y quadruple prime minus y, and set it equal to the Laplace transform of 0, okay, then what happens is this is nothing but the Laplace transform of y quadruple prime minus the Laplace transform of y, which is equal to 0. Okay, the Laplace transform of 0 is 0. Okay, so then this is what it means by being a linear operator. Okay, so that's what it means. Now we apply the same theory, assuming that the function that we're going to find y of t applies and satisfies all the conditions aforementioned. Okay, so what we're going to do is we're going to represent this in terms of the Laplace transform of y only. So then from this we have the Laplace transform of y, okay, of t multiplied by s to the nth, right? Now we're taking the Laplace transform of the fourth derivative of y, so then n is 4 for the first one, so s to the fourth power. Okay, then we subtract y of 0, okay, times s to the third. Okay, so you see the pattern here is actually analogous to binomial expansion. So what do I mean by a binomial expansion? Is basically when you say a plus b to the power of n, right? You have to use Pascal's triangle in order to expand a binomial. So you do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. And so what happens is, as you can see, the powers, okay, of the first is going to have to decrease from n to n minus 1 to n minus 2, and so on. While the powers of b will start to increase as the powers of a decrease. So over here, the analogy is the powers of y of 0 start to increase by 1, while the powers of s start to decrease by 1. So over here, clearly, the power of y is 0, right? Well, the derivative, the nth derivative, right, will be nothing, so there's no derivatives here. But there's s to the fourth. Now over here, we start to see the function y, okay, with the initial value, y of 0, okay, which is the first derivative, times s to the third, so we're subtracting 1. So with this pattern, we know that the next one has to be the first derivative, okay, of y with respect to t, evaluated at 0, times s squared, right? Because we're decreasing the powers of s, increasing the derivative, the nth derivative of y. So then minus y double prime of 0 times s minus y triple prime of 0. All of that's equal to 0, okay? So then what we want to do next, oh, excuse me, I forgot to take the Laplace transform of y, which is just the Laplace transform of y. So minus Laplace transform of y, all of that is equal to 0. Okay, so now let's say, okay, for simplicity's sake, that the Laplace transform of y is nothing but big Y of s, capital Y of s, in such a way that if we take the inverse Laplace transform of both sides, so if we take the inverse Laplace transform, we get the function y of t. So we get inverse Laplace transform of big Y of s, okay, which will give us the answer, okay, to the differential equation, the solution. And so over here what we gotta do is we gotta factor, okay, the Laplace transform of y of t. So we factor that s squared minus 1, so we have s to the fourth, minus 1 times capital Y of s, okay? And then we can move everything else to the other side. Of course, taking advantage of the initial value problem. If you can see, all the values for all derivatives except for the first derivative are 0. For the first derivative, it's 1. So y prime of 0 is 1. So clearly, this goes to 0, this goes to 0, and this goes to 0. So then, over here we have 1, so 1 times s squared, negative s squared. So then we have that all of this will be equal to, okay, in this case will be positive, right? So we add it on the other side, so we have s squared. So it's much simpler, well, given the initial value problem, of course. If we were given different values, it would be a little bit more hairy, but you know, for the purposes of this problem, it's simpler. So then we have that capital Y of s is nothing but s squared divided by s to the fourth minus 1. And so now the next thing we gotta do is we gotta split this up. So we gotta decompose it into several fractions. So this is nothing but s squared divided by s squared minus 1 times s squared plus 1. Okay? Now we use the method of partial fractions. So then we say that in this case, okay, s squared, okay, s squared is going to be equal to, well, s squared divided by s squared minus 1 times s squared plus 1 is nothing but a times s plus b divided by the first, okay, factor in the denominator, which is s squared minus 1, so s squared minus 1, okay, plus abcs plus d divided by s squared plus 1, okay? Now we find the common denominator, right? And then we're left with something like this. So we multiply over here by s squared minus 1, right? So we get rid of that, and we multiply over here by s squared plus 1. Okay, so then we can cancel out the denominators. Now we can simplify this a little further by getting two different equations for which we can solve for the values a, b, c, and d. So for example, let s equal to 1 and negative 1, right? Because clearly over here, s equals negative 1 and 1 gives two different values, but two different equations that are quite similar. So then we get that s squared is nothing but, okay, if we substitute s by 1, so we're going to get a plus b, okay, multiplied by 2, plus cs plus d, and then what happens here when we substitute by 1? Well, this just goes to 0, right? So we're left with this over here, okay? Okay, of course, clearly the factor of s to the 0 is just going to be equal to 0. So we said 2, okay, times a plus b equal to 0, okay? Now, if we let, in this case, if we let s equal to negative 1, what's going to happen is this becomes, this over here will become 0 again, right? So this goes to 0. So then what we're going to have is that this becomes, I mean, it's pretty much the same thing if you think about it. So maybe we should look for a different number. So let's say, how about s equals 2? So if s equals 2, okay, then we're going to have, oh, I'm sorry, my apologies. Over here, there's a mistake. We said s equal to 1, so this has to be 1. Okay, so that's going to be 1 over here, 1 squared, so that's 1. So now if we let that equal to negative 1, we should get the same thing pretty much, right? But now what happens is this becomes 1, right? negative 1 squared, but now the a has a negative in it. So it's going to be 2 times negative a plus b, okay, equals to 1. So we have two different equations where we can find, okay, what a and b is easily. So if we solve this, we just add them together, right? So if you add them together, what you're going to find is that, okay, 2a minus 2b, excuse me, 2a minus 2a is 0. This cancels out. While 2b plus 2b is 4, right? So then b is going to be 1/4, right? All right, so if that's the case for this, okay, now we just found b. But we would also like to find what's going to be, in this case, c and d. So for that, we're going to say, for example, s equals 2. So if s equals 2, okay, s equals 2, okay, so, we didn't find a yet. So let b equals to 1/4, right? So in that case, if b is 1/4, then what we're going to have is that 2 times a plus 1/2 equals to 1. 1 minus 1/2 is a half, right? So then we get that a is also 1/4. Okay? And you can clearly see that by just testing, okay, some values over here. So 1/4 plus 1/4, right, gives you a half. A half times 2 is 1. So that works, right? But it does not work for the second equation, if you see. Okay, so, okay, so here's the mistake. Here we have to have 2. So it's going to be b is equal to 2/4. So that's nothing but 1/2. Okay, so yeah, that makes more sense. My apologies. So then what we're going to have is 2a plus 2 times 1/2, which is 1. So then a is 0. Okay, for that matter. Okay, good. Now let's test other values. Okay, so let's say that I don't know, s equals to 0, right? We didn't try s equals 0. We're trying to find easy numbers. So if s is 0, we have 0 is equal to 0 plus b. So we know that b is a half, right? So half times 1, okay, plus d multiplied by negative 1. And here we can find d easily. So d is going to be a half. Okay, so if that's the case, we can find what's going to be c. Okay, so we can go back and let's say 2, right? So if s equals to 2, okay, but I think, yeah, in that case, if s equals to 2, then we have s squared, which is 4. Okay, and that's going to be equal to a times s, but a is 0. Okay, so we don't write that. Plus b, which is 1/2, times 2 squared, which is going to be 4, plus 1 is 5. Okay, plus c, we know c is going to be, c is what we want to find. We know d, so we have plus c times 2, so that's going to be 2c plus d, but that's going to be 1/2, multiplied by 4 minus 1, which is 3. Okay? So now 4 minus 5 halves will give you 8 minus 5 was 3 halves. Okay, 3 halves divided by 3 is a half. So you have 1/2 equals to 2c minus 1/2. So c equals 0. Oh no, c is equal to 1 divided by 2, which is 1/2. So c is a half, d is a half, b is a half, but a is 0. Okay. Okay, so now we found the expression for the Laplace transform of y of t, which is a half over s squared minus 1 plus a half over s squared plus 1. Okay, so now if you observe, right, you know that if you take the inverse Laplace transform on both sides, you get the function y of t. So therefore, if we take the Laplace transform on both sides, we get that y of t is the inverse Laplace transform, okay, of 1/2 over s squared minus 1 plus 1/2 over s squared plus 1. And now, well, this is just a matter of like if you know the Laplace transforms by memory, or you could just like look them up on the table. But I will show you how to derive the Laplace transforms for each of the following. So if you know, this one over here will give you sinh, okay, half of sinh of t, and this will give you 1/2 of sine of t. So then we find that the solution to the initial value problem is 1/2 of sinh of t plus sine of t. But I'll show you how we come to that. So if we take the Laplace transform of sinh of t, okay, then we have to take the integral from 0 to infinity of e to the minus st times sinh of t dt, okay? And of course, if you are doing an exam, you want to make sure that you rewrite it as a limit. So limit as a goes to infinity, the integral from 0 to a of e to the minus st sinh of t dt. We use integration by parts. We can differentiate e to the minus st, we can integrate sinh. So we do tabular integration, that's the easier way to do integration by parts, where the differentiation goes to the left and integration on the right. So then we have sinh over here. We do a table. This is positive, the next one is negative, and the next one is positive, and so on. The derivative of e to the minus st with respect to t is minus s e to the minus st. And then we differentiate that again, we get s squared e to the minus st. Now the integral of sinh is cos of t dt. Integral of cos is sinh of t. So now we cross multiply over here, and then we multiply sinh by s squared e to the minus st and integrate it. So therefore we have that, we're going to call this the Laplace transform of sinh of t equals to, well, we have e to the minus st, we can factor that out, and we have cos, okay, we have cos of t plus, right, negative times negative is positive, and then we have s plus s sinh of t, okay? Of course, we're going to add s squared multiplied by the integral from 0 to infinity of e to the minus st times sinh of t dt, which is nothing but s squared times the Laplace transform of sinh of t. So this is s squared times the Laplace transform of sinh of t. Okay, so that from that we can subtract s squared Laplace transform of sinh on both sides. We can factor that, and we get that the Laplace transform of sinh of t is equal to, well, the limit as a goes to infinity of e to the minus st, okay, times cos of t plus s sinh of t divided by 1 minus s squared from 0 to a, right? Now when we evaluate the limit at infinity, what's going to happen is that e, the exponential function, is going to be dominant, and therefore if it goes on the bottom, right, this is basically a negative exponent, and so when we have negative e to the negative infinity, we get 0. So we get 0, the Laplace transform sinh of t equals to 0 minus, we evaluate the limit of the lower limit at 0. So we substitute t by 0, e to the 0 is 1, cos of 0 is 1, and sinh of 0 is 0. So again, we get 1 over 1 minus s squared, which is nothing but 1 over s squared minus 1. And essentially, the Laplace transform of sinh is here. So we take the inverse Laplace transform of this, and we get sinh, okay? So then, well, the Laplace transform of sine of t is quite trivial to do. It's pretty much the same process. You could try it on your own. So that is left to you as an exercise, okay? So here is the answer to the initial value problem of the differential equation. Thanks for watching, and I'll keep posting more videos on differential equations. Take care.